Welcome to what is it? Physics 4B. Okay. If Zachary can turn off the. Okay, very good. Basically, this is the live session for this. This is the first live session. We're going to be holding live sessions for every time we're supposed to meet. Had we met in basically face to face. You are actually required to attend those live sessions, but if you cannot make it, I record these sessions and I post them on YouTube. And then the minute they are posted on YouTube, actually, if you subscribe to the YouTube channel, you're going to get in notifications. I will try to clean up those things because with the closed captioning and all of that takes a little bit of time. Once that's ready, I go actually and put it on a discussion session in our course on Canvas, so that if you missed the class, if you missed the live session, you still can go and watch that live session. The reason why you need to do that is because there is a discussion that follows after that live session, and that discussion is graded. There will be at times, at least probably not today, because the warning did not go out yet. There will be questions inside those live sessions. If you attend them, you're going to see them. If you miss that live session, you can go and watch it on YouTube, where there will be questions. Like, for example, we have discussed a problem, and this is the answer to that problem. During the lab session, we go through that specific problem, we solve it, we have the answer for it. All I am asking then is just to give me the answer to it. So you're not going to do the whole derivation again and say, okay, this is the whole thing. And no, just the answer. Just to prove to me that you're actually following. This goes towards your participation grade. And the participation in physics is a crucial, actually in anything is crucial. But if you don't participate and you are an observer watching things happening in front of you, you're not going to learn. That's at least what research has indicated, that people learn better when they actually do things. Okay. Again, for those who joined us late, can you turn off, please, the microphones, because okay, just to make sure that unless you have a question and you cannot type it or something, then you're welcome to turn on the microphone and ask these things. With a thumbs up, I hope that you guys understand at least this part in here. Do I get feedback from you guys that this sounds right? The promise is you attend or you watch the session if you cannot make it, which is fine, but you're going to go back and basically go through those things, go through the exercises we do in class to make sure that we have that understanding. Okay, so I'm going to start basically by telling you, I guess I introduced myself enough to you guys via the emails I sent. I sent one, I think, about a week ago, and I sent one yesterday again. And basically, I'm going to be your instructor for Physics 2. That's how it's introduced at times. I taught this class for many years, actually, in different places. So at times, I sound kind of basically memorize these things. So I'm hoping that you stop me and tell me to explain something if it goes too fast, okay? So I want you to understand that thing there. Now, let me go into the syllabus, which is really a good starting point, that I'm hoping by now that everybody had a chance to look at it. So let me share my screen. And here is the syllabus for Physics 4B. Again, I need to have a verbal now confirmation, at least from one of you guys, that you can see this, that the screen is shared. Okay, very good, very good. At least a few people did the thumbs up. Very good. So basically, like I said, this is the syllabus for the course. There are things that you really need to be familiar with. And one of the things that you're going to be doing in here when you come to this course is to see what kind of requirements I do have for this class. I already posted something for the homework, because there are two components for the homework that you need to be aware of. One, using Mastering Physics. That is questions basically from there. This is the online version of the homework. Usually It's probably between 15 to 20 problems. Most of them should be easy enough to be done quickly. Some of them you may have difficulty with them. Please let me know on those so that we can work them out. I noticed in the past that there were problems in those online homework problems. You do the problem and it's correct, 100% correct. And the online tool will tell you that you got it incorrect. Please email me right away when that situation happens, okay? Tell me I did this problem, I'm 100% sure it's correct, and the system is grading it wrong. So in this case, we go and override that one. Okay, that's one part. The other part is, there is another type of homework which is gonna be turned in, and you already have an assignment on that from chapter 1. I extended the due date for it a little longer so that you understand what that is. That's 5 problems, not too many, that you're going to turn in on Canvas. The way this works is the following. You will have 6 components that I need to see in your answer. Those 6 components are the following. The first component is a restatement basically of the problem based on the information that was given to you in the problem. This is what we know from the problem. This is what we were asked from the problem. So that's basically a translation, if you wish, of the actual problem into stuff that you already say. For example, the mass is so-and-so, the charge is so-and-so, and things like that. So that's step 1. Step 2, then, you go and find other things that you're going to be using. For example, I know Coulomb's law in this case will help me solve this problem. We know Coulomb's law. That's something that is a foundation. Okay, I know F equals to ma, for example. That is something that is going to help me solve this problem. So those are the things that I can pull to solve this problem. I know also the geometry in here is involved. I'm going to use this configuration and this identity. So those are the things that I'm going to pull again. Now I go and solve this problem step by step. That is now step 3. So I'm doing now the third one of the 6 components that I need for my homework solution. I do that step by step, and every step, that is the 4th component now, needs to be justified, whether from physics, whether from math, whether from geometry, or whatever other source in here, the justification for this. This is to show me and to show yourself first before me that you really are mastering this topic. You know exactly the steps. You know what kind of justification is happening in here. So to build confidence in your solution and basically justify it, I need those 2 things. While you're solving, justify your steps. So those are 2 essential components that are needed. You may come in and turn in a solution from top to bottom as if you're doing a math exercise, basically without justifications. It's true, I mean, you might find the correct answer, but you're not communicating to me or to anyone else that knowledge. I need to see that in the 4th component, namely justification. So that's another component that is there. The final one, now you have solved the problem, is to state the answer. Remember from step 1, you were supposed to find answers to specific questions that were asked in the problem. You need to come now to this point in here, which is step 5, element 5, and tell me the solution then, or the answer to that question is, based on your solution, is the following. So now we fulfilled 5 out of the 6 requirements when solving the homework problem. The 6th one is going to think about what this means. Does it make sense to you? Can you pull any information out of it? Can you justify other things? Discuss your solution at the end. So I need to see the 6 components and every one of those homework problems I gave you to turn in by themselves. The reason why I did that is, in the past, at least before the advancement of the internet and the availability of resources, people will really struggle through solving homework problems and may or may not find answers. Nowadays, you can check resources and basically have the answers. And if you don't express that knowledge, if you don't show me that you really know these things, it's hard, because you may find a solution from some source which you are not really discouraged from doing. That's fine. That's part of the process. You cannot solve a problem. You contact one of your peers. This is ideal, actually. I love that. This is part of the process. You contact him or her and develop a working process, and you work together on a solution of the problem. If you want me to facilitate that, that would be great. I will facilitate it, and you can work together. There is no problem with that. Now you cannot find a solution. You go and check on a resource somewhere else online. That's great, but you have to understand what you're writing. That's what I'm after. You have to know what you're doing. That is really what I want to see through that process. Does this sound right? Yes, or need to explain a little bit more about those components. As we move along, it's going to be clearer and clearer. As a matter of fact, in the homework, there is a rubric that explains exactly what I'm talking about. So you can go and follow the rubric and basically check mark things. 1, 2, 3, 4, 5. So before me putting a grade for you, you know exactly how much you're supposed to get in that assignment. And that should be true for everything, not just for the homework, also for labs, for everything else. Yes? Okay, very good. So this is the two components of the homework. They weigh exactly the same thing, are going to be added toward your homework grade. In addition to the participation, which we already talked about, okay? Is this your class? I think I may have made a mistake. Yeah, I think this is your class. This is fine. I'm sorry. Yeah, I thought for a second that okay, so the exams with the final are worth 35 points. The homework is worth 15 points. I think there is something. Yeah, hold on. I think there is something wrong in here. I need to fix this, okay? I think I didn't copy it right. But I will publish it hopefully by the end of the day, okay? You will have an updated version of this thing in here. 35, 50. Yeah, there is a component that is missing in here, okay? So I need to fix that. I'm sorry about that, okay? Now, this is basically the course sequence that you guys have. This is where we are supposed to be every time in here. There are 4 exams in this class, okay? 4 exams plus the final in this class. That I know for sure, so you have to pay attention to that. The exams are every 3 chapters are 1 exam, except the last 2 chapters, chapter 30 and 31, are only 1 exam. So you count it, 21, 22, and 23, they are 1 exam. 4, 25, 26 is another exam. 27, 28, 29 is another exam. 30 and 31 is the last exam. Those are 4 exams, plus the final. The final is comprehensive. Now, if you miss one of the exams for one reason or the other, it doesn't matter what that is, you're going to get a 0 in that exam. So please do not miss an exam. It's very important that you do all of your exams. However, and that's really the phrase to catch this last statement, is one of this 5 assignments, namely 4 exams plus final, will be dropped. The lowest of which of these things will be dropped. So if in case you miss that one in a specific exam or the final, you know that specific assignment is going to be dropped. So try not to miss anything, at least in the beginning, until you know your grade is going to shape up exactly where you want it to be. Then you may probably drop that one in there if you want to, okay? Same thing is true for the homework, by the way, in terms of dropping the lowest grade. And then not accepting any non-work. Somebody has posted something in here in the chat. All exams will be during the day of the class, okay? So basically, it's not specific hours during that day. We're going to come to the details on how these things work, okay? So that's a good question by Carlos. So in terms of the lowest grade being dropped from the homework, from the labs, and also from the exams, and not accepting any late work or not doing any work, so basically getting a 0 in it. So you have to really adhere to the deadlines and all of that, so that we are all on the same page. Participation, like I said, has this discussion things that you already are aware of, that either you attend the live session or watch the recorded sessions, and then answer those specific questions. It tells you there were problems that were specifically related to the discussion today. They may be 1, there may be 2, there may be 3. I cannot come in here, for example, and start the session and right after the 15th minute and tell you, okay, here's a problem. Then after that, I see an exodus. No, there might be another one down the road. So you really need to stick around and follow and do the examples we do together toward the end. Then you know there were 3 examples. Here is the answer to the first one. Here is the answer to the second one. And here is the answer to the third one. Okay. So that's participation grade. There was also an assignment that you already have received. And the assignment is to introduce yourself. That's also graded, by the way. And the rubric is also published with it. So hopefully you can go to those 3 points on the top in there and basically bring from the drop down, basically the, not in here, I guess I'm not in an assignment to do that. The rubric and see exactly how you're going to be graded for that. Basically introduce yourself, picture yourself, and also there was a question there, if I remember, on the 4th law, or was it the 3 laws of Newton, and why, because the promise there, you guys took physics 4A, is that once you learn 3 laws of Newton, that's all you need to solve any problem in physics. So the question is, why in the world do we have to go past beyond chapter 4 then in the book? If that's all we need, we learn them, we know them. So why do we have to go past that point? I want that question to be answered from you guys and have a discussion on that. Other people will reply to you and hopefully we'll have a discussion going in there just to make sure everybody is on board and actually participation in the class. There was another question which I forgot now, since you guys are, because you have a choice between one or the other, so you're not supposed to do both of them, okay? Okay, so the other question was, okay, yeah, this is actually a good question too. Mr. Newton explained Kepler's laws. Kepler spent so many years basically working on his 3 laws, and you did that also part of physics 4A. And then Mr. Newton, basically after the plague that hit London, was sent home like everybody else, like what we're doing right now. We are in a pandemic when everybody's sitting at home, and he was given Kepler's laws, and he was told, okay, can you explain Kepler's laws? And of course, he came up with a wonderful explanation using his mechanics, basically based on the force that is existent between the different bodies in the solar system and so on and so forth. So he came up with an explanation. Well, I have another explanation for the same thing, okay? Namely, there is a ball in there, it's in the middle of the solar system. So if you're wondering where is that ball, you cannot see it. That's part of my theory, okay? You cannot see the ball, but where all of the planets are sitting on its horns and the ball is spinning, and so that all of 3 laws of Kepler are working. So why in the world my theory is not good? That's one explanation. There is another explanation that I have in there too, involving angels and things like that. So you can do that too. I mean, I can come up with as many explanations as possible as you can think, but there is a flaw in my approach than that of Newton. So I want you to think about that and give me yes. Are the lab sessions recorded and posted, and also do you give? Okay, the lab sessions will be recorded, that's Jesse, and posted also, the same thing. The same thing applies also for the lab and the lecture in terms of participation, so the same thing. They give partial credit on quizzes, and quizzes, no. When you have a quiz like multiple choice quizzes, there is either you get it right or wrong. But when we're talking about exams, yes, and tests, yes, there is partial credit, okay? So let's talk about the exams, because somebody else also asked another question earlier about that. 4 exams, as I said, and the final. Well, the exams are not going to be testing you on how well you do in terms of searching for answers from Google. I would not recommend that, because if you do that, you're going to waste time, and time is valuable. So once the exam starts, once you start the exam, you have a very limited time to finish it, so you better get going and doing the actual exam. So that's really my question for you. If you start seeking help from other people also, you're going to be wasting time. But there are reasons for that, 2 reasons. First of all, your exam is unique. So you're going to have your own different exam than other people. So you cannot really find that. That's one reason. The second reason is the exams are made in-house. So you're not going to find them somewhere else. As a matter of fact, you are urged to follow the steps, step 1, step 2, step 3, and basically solving those exams. They are not foreign to you, the exams, though. They are coming from the book, in a sense. But as long as you follow the steps, you should be fine. Because by the time you waste it and start looking for resources, you might find out that time is running out and you better put something together, and you'll be frustrated. And the next thing is, think of them as take-home exams. In the past, we used to do take-home exams too. So this is no different than that at all. So they are not necessarily a challenge, but they're very much doable if you follow the steps, and usually the time allotted for them is exactly what needs to be done for them. If you start wasting time left and right, you're going to find yourself losing time on those. So that in terms of the exams. However, as a question was asked by Jesse, yes, I do give partial credits if in case you show progress toward the answers. In terms of technology, any other question related to these things before we move on? No? Let me check the chat in here. There is nothing new. Okay. In terms of technology, it's a good idea to be very much familiar with technology at this point, because everything we're doing relies extensively or heavily on it. So I recommend that you guys do that as much as possible of that. The software I'm going to rely a lot on is by Adobe. So I'm going to put it in the chat right now. I don't know if I put it on. It's get.adobe. Oh man, I forgot the A. I think Adobe /reader. Let me make sure the link works for me first before I post it for you guys. Okay, so I'm going to open a new tab in here. Oops, I put it, yeah. So when you put get Adobe Reader, it takes you to get.adobereader.com from the website of, let me follow this link in here. Let me open it first. I don't want it to be taken to. Yeah, this is another thing. When you're when you're online, you have to be very, very smart about it. Don't go to third-party vendors and try to download things. Okay, go to the, I forgot the .com earlier. So this is the link, okay? Get the Adobe Reader. I need the Adobe. It's it's 100% free software. So please do that, okay? So that is one thing that we will be needing for this class, because for the lab specifically, you will have fillable PDF files, and I'm going to talk later on down the road on the labs when it comes time to it, on how you do that. You will have PDF fillable files. Now, everybody thinks that they can do PDF for you, and including all the browsers, basically. Chrome, Firefox. I'm using Firefox for this specific class. And also Internet Explorer, and also the other one from Safari, and everybody. Don't use none of them, because when it comes to a PDF fillable file, the safest bet is the Reader by Adobe itself, and the Reader will fill the data for you and then saves that data back to the file, and then you can upload the file. So you will be, in the assignment itself, you will be given a PDF fillable file that has the instructions and also the response to those questions that are in the lab. So you're going to go through the lab step by step, fill the answers, fill the tables. Now, when it comes to graphs, you will need also Excel, okay? Microsoft Excel. If you choose to, you will also need Microsoft Word. I don't really necessarily use it as much, but those are the two softwares you will need. They are 100% free also for students attending the college. That's part of the deal Microsoft gives for education. So please take advantage of that and use those software. Now, if you say you cannot do those for one reason or the other, there is Openoffice also that does these things, okay? That's a free also, 100% free, so that you can use. You will see the labs using something called Geogebra. So I want you to also be familiar with that. This is some simulation that I personally will go and basically simulate the entire lab situation for you guys, and you're going to be doing it. As a matter of fact, I also use it in lecture. Geogebra also is free. So everything I'm giving you in here is 100% free, does not require from you any investments whatsoever. So you can go get going with these things and download them and start using them, okay? So this is in terms of the technology and in terms of the basically course requirements. We talked about that. Let me go back into the course. Where is your class? Is this class? Yeah, I think this is class, yes. Where were we? Home. So the recordings, everybody should be in the models, okay? I don't want to click on the models right now because if I do, it's going to take me to the teacher's view, which has a lot of things that are not at this point ready. So I don't want them to be seen, but hopefully you are already there. One of the things that is there already is the, let me see if I can switch to student view. That should give me the access to it as a student. Student view. Yep, I think it does. Okay, so those are the things I'm going to be looking at if I am one of you guys. The first thing is the community rules. Please observe those rules. And the second one is this assignment that we talked about at this point. I'm going to submit my assignment in here. And I'm going to go back into next. And here. Next takes me to the stuff that is more or less the summary of this chapter. Okay. And we're going to discuss this chapter more in detail in the recordings. And finally is going to take me to the homework assignment. Okay, we talked about. Okay, and why is it not showing? This assignment is will unlock on the 26th because we are on the 24th. So by then you will see the assignment, the problems basically. As a matter of fact, they are here. Okay, problem 74, problem 79, problem 83, and 95 and 96. Okay, and this is how they are graded. Any questions? Let me stop sharing right now. Any questions from you guys? Alex, can you turn off the camera, please? Okay, very good. Okay. Any questions so far? Okay, that's a good point by Christopher on those things. Okay, yeah, vendors, I mean, of software, they always try to bundle all the things with their free offerings. So Christopher is 100% right not to download other things other than just what you absolutely need, which is the reader, because those things tend to slow your software. As a matter of fact, I refrained myself recently from using Chrome because Chrome tend to slow down my computer, so I'm not using it anymore. That's why I'm using actually Firefox. That's a very good point. Okay. Okay. If you guys don't have any questions, that we can start with the class then. This session will end at 2:10 or 2, what is it the time? Yeah, 2:10. And then we're going to take a break. We're going to continue for the lab. Again, we're going to continue with the content today. And down the road, we're going to have more, the activity, the actual lab will start Monday, a week from today. Okay? So the lab session, probably we're not going to have the entire lab session because it's going to last forever. And by probably after 1 hour, you guys are going to be tired and I'm going to lose my voice. Okay? So let's share my screen and let's find where the thing I need to share is. So this is basically the content for chapter 1. And before I do that, let me ask you, and you can insert this in your, some people are having difficulty or what? Because I'm receiving messages from some of your classmates in here. Okay. And I know there are more students than what we have right now. And that's why probably they're having, so we're going to answer them later on. Anyway, I'm going to ask you a question. And you can answer it in the messages in the below, or you can turn on your audio if you like. What was the main thing you learned from Physics 4A? The one thing. Anybody? Gravity. That's a good point. Okay. Anybody else? The law of gravity. The question was, I'm going to type it in here. What did you learn from physics 4A? The reason why I'm asking that, because I know for a fact that you did take that. Oops, I sent it to only one person. Let me send it to everybody. Sorry. Everyone. Okay, that's good for us. That's a very good point too, okay? Okay, Alex told me F equals to MA. Can I second Alex and say that that's probably the most important thing that you have learned? Any objections? No? That was the most important thing that you must have learned in physics 4A, because that law summarizes everything that you can basically do with physics. And that was one of the prompts there actually in the discussions, is this Newton's laws. This is the second law of Newton. Here is the promise of that law, basically what it tells you. What does physics ask? Basically, it's all about future. It's all about predicting things, okay? All about predictions. If you tell me what all the forces are, basically, that are exerted on an object, I can invoke this law and find the acceleration. And once I find the acceleration, basically, I can integrate the acceleration and find the velocity, find everything there is to know about that object. So that was really by far the most important topic. Now, I'm going to ask you another question, and already one of you has answered it. I think Carlos answered about the law of gravity, the force of gravity. What kind of other forces do we learn also in that class? That's the follow-up question. So the main thing is F equals to ma. We learned F of gravity, and we worked with the gravity on an inclined plane. We did so many things with that, okay? I remember I didn't teach you that, but I know for a fact you must have done that. So what kind of other forces that you learned in that class, other than the force of gravity? Gravity was one. I just need another one. Tension, okay? That's very good, okay? That's another. Acceleration is not a force, by the way. Acceleration is a, okay, the spring, magnetic force. Did you do that in physics 4A? Nagata? Okay, because that's the subject of this class. That's the subject of physics 2, okay? Normal force. So those are forces that you've learned and you all applied in there. Today, the purpose of physics 2 is to introduce this new force. And that's exactly what we're going to be doing. So this force is an electrostatic force. Okay, that's good. Okay, Nagata is remembering things from way back when he was in kindergarten. I'm sorry, high school. Sorry. Okay. So let me share the screen with you guys. And this is the force that we're going to introduce. It's the electrostatic force. The thing that you really need to pay attention to is the terminology. So what I'm using in here, electrostatic. So I'm talking about charges. So we need to know what charges are first. And we're going to talk about that. And then once we know that, then we're going to, I lost my hair. I cut my hair, so I don't have much hair. So if I rub anything on it, I don't have any force whatsoever. But you're familiar with the law of basically this experiment. So if I take I need to do more of this, okay? It attracted it, okay? I don't know if you can see it or not, the screen. So this is the electrostatic force. Think about this force. The entire Earth, it fell now. The entire Earth is pulling on this piece of paper, yet with just scratching a little bit of this ruler, I was able to create another force that was not discussed in physics 4A. And that force is what we're talking about now, the electrostatic force. So people before Mr. Coulomb, they were experimenting with this force, with this idea. And they were doing all kinds of things, taking metals, taking non-metals, this is actually non-metallic component, and then playing with them, charging them, rubbing them, seeing the discharge of the clouds, for example, during what is it? Oh man, the word escaped me now. Discharge of the clouds. What is that? The lightning, okay, when it strikes, and so on and so forth. So those are electrical phenomenon, and they needed to be explained. Parallel to that, people also knew about magnetism, which is a completely different story. Magnets, for example, they attract one another, they repel one another. The same thing is true also for the electrostatic force. So people trying to explain these things. And Mr. Coulomb basically summarized all of their work in one law, basically, and that's the beauty of it. In prior courses, you've learned what the law is. Can anybody tell me in a nutshell what a law is? What is a law?
Isn't it basically like a fact, a series of, it's a theory that's been tested multiple times and basically almost proven?
That's very good. The key word that you use is tested, okay? So it has been observed experimentally. So when you learn the 3 laws of Newton, that's it. That's all the laws in nature needs. Doesn't need no more laws. So if an officer tomorrow stops you and tells you that you're in violation of the law, you have to specifically ask him which one of the 3 laws he is talking about. Because there is no way you can violate any law, okay? Is it clear? Tested? I mean, don't do that, okay? If you tell him, probably he thinks that you're making fun of him or her, okay? So don't do that, okay? So the point being in here is the key word is test, observed, okay? So that is the key word in here for this law, day in, day out. So Mr. Coulomb, basically after coming up with that observations, he put them together into one law that basically charges of the same type, we know that they repel. Charges of different types, they attract. The strength of the force of attraction. Because all you have to do is nail one of these charges to the wall or to a fixed place and bring the other charges and attach to a mass spring system that measures forces, like this one, okay? That measures forces. Okay, with the window. I think I need to, so once it's being pulled on one side, I can see the reading of the force, how much it is. If I put more charges on one of the charges, then this stretch will be more. And how much it's more? It's proportional, actually, with the same quantity. So if you double the charge, the force doubles. If you triple the charge, the force triples. If you halve the charge, the force halves also. So we know it's proportional to the charge. Also, if I bring the charges closer by twice the distance, I mean, if I bring them closer by half, basically, the force quadruples. If I move them away, double the distance, the force drops by a factor of 4. Okay. No, that's it. That's the one note only. I'm just going through basically the. I don't have any PowerPoints. I usually don't do any PowerPoints for calc-based courses. So if you're expecting that, I'm sorry. Okay. So that's it. That's basically the whole thing. Okay. Yeah. So we're gonna go and we're gonna type in here. Okay. So let me pull my pen in here and express the law. And that's why it's a very good, very important thing that you guys need to be taking notes too, even during lecture. Okay. Especially during lecture. Okay, where is my pen and drawing here? Okay, so this is the law now that we're talking. This is a vector force. Okay, so the force is not a scalar; it's a vector, and you discussed that in physics 4A. What is a vector and what is a scalar? It's 1 over 4 pi, that's a number, that is the 4 pi usually has to do with the sphere, basically the area of a sphere, times the property of the medium where you do this experiment. Property of the medium in here is called permittivity. If you do it in vacuum, there is a number for epsilon naught. If you do it in in water, for example, there is a different number. So this experiment depends on the medium where you put it, and the medium is expressed in terms of this factor in here, epsilon naught. Okay, this is called the permittivity. So this is basically permittivity. Okay, times the product of the two charges. So I'm assuming in here that I have two charges, Q1 and Q2, put them next to one another. So this is, they're proportional. If you double one, the force doubles. If you half one, the force drops by a factor of half. That's why there is a one-to-one correspondence with it. Divided by the distance squared. Okay? The distance between the two squared. And then there is another quantity in here I'm going to throw in, because this is a vector. We need the direction of the vector. The direction of the vector expressed by the r hat in this case, which is the unit vector. So let me represent this force a little bit better. Okay, you come in here, I have to add another slide. So this is what I'm assuming. Okay, this is how the law is stated. So I have a charge 1 in here, I have a charge 2 in here. So this is my Q1. This is my Q2 charge in here. The distance between these two charges is R. Or if you want to put it, the distance between point charge 1 and point charge 2 is expressed in terms of the unit, in the terms of the vector R12, as opposed to the vector that links 2 to 1, that would be R21. So there is that notation that I'm using in here. The vector that leaves 1 to 2, I'm calling it R12. The vector that leaves 2 to 1, I'm representing it R21. So there is a distinction in here you really need to be paying attention to. The unit vector I'm talking about, this is R hat. This is R hat for 1 to 2. This would be R hat from 2 to 1. So if my focus is on charge Q2, for example, and my goal is to find the force on Q2, then according to this representation, the force on 2, due to the charge that is sitting in R1, so again, it's going to be 1 over 4 pi epsilon naught times the product of the two charges divided by that distance, which is, doesn't matter which one I use because it's a distance squared, okay? But the unit vector now matters. The unit vector now matters. This is the force on 2, okay? This is the force on 2. It's in that same direction from 1 to 2 hat, okay? Now somebody asks, okay, that is if the two charges are positive, it's true, okay? Or the two charges are negative, it's true. But if the two charges are different size, then algebraically, this number yields a different sign. Do you guys understand? Q1 times Q2 will be negative, and if Q1 times Q2 will be negative, this whole thing will become negative, and the force will point in the opposite direction. It's going to be this way. That is if the two charges have opposite signs. You guys understand that? Let me undo that last thing in here and try to choose a different color just to make the distinction. So if the two charges are different signs, the forces will be in the opposite direction to R1 and R1 hat or R12 hat or R21 hat, okay? And the two forces will be attractive actually, because this whole thing becomes negative, because Q1 times Q2 will be negative if the two charges have opposite signs. If the charges have a positive signs, or same signs, as long as their product is positive, then the two forces will be as indicated by the hat unit vectors. Okay, so this is Coulomb's law. You really need to practice this law, and we're going to do that as much as possible. Okay, there are some basic laws that we have to understand in terms of this Newton's laws. Coulomb's law. Mr. Coulomb, of course, when he basically put it in this statement, he didn't really call it Coulomb's law. It was other people who came after him that they called it Coulomb's law. And honestly, most of what Mr. Coulomb did, and he did a lot of work too, was the biggest thing that he did actually was to put all of the other people's work in and summarize them together and put them all in one place together and put them into the terms of this law that we're going to be using extensively in this class. Of course, if we try to understand where the charge comes in, And there were so many experiments later on to determine the nature of charge, the electrical charge. One of the things that we basically, and that was actually an accident of later, basically, because we noticed the electric flow that goes in from one direction to the other. We gave a sign for the direction of the current. That sign resulted in a representation that now we have, that the atom is made up of basically three. That's basically, if you want to understand, and for some of you who took chemistry, you have a little bit of understanding of that. So it's made up of a nucleus that has positive charges in it and neutral charges, neutrons, and also have negative charges in it for the electrons. Okay, so the electronic cloud has a negative charge, the electron is negative, and the proton is positive. Had we chosen the other direction for the current by convention, the electron would have ended up with a positive charge, and the proton would have ended up with a negative charge. So it's a matter of convention. There is nothing intrinsic about the electron having a negative charge or having a positive charge. If tomorrow we're successful in communicating with another civilization somewhere else, they may end up having chosen a different signs for the electron and the proton, and they would probably have a better go at it, because now everywhere we try to write stuff that has to do with chemistry or physics or things like that, we deal with, most of the times, all chemistry actually deals with the electrons. So they spend most of the time adding that extra minus sign, which is kind of an annoyance, but I guess we got used to it in here. Okay, but just this is some of the properties of this three things in here, which you really need to have a rough idea of how much they are. The mass of the proton, the mass of the electron, and the mass of the neutron. Neutron and proton have similar masses. The only thing is, neutrons do not have a charge. So they don't play this game. They're completely basically non-participants when it comes to Coulomb's law. The only thing that plays a role in this case in here are actually as a matter of fact, the electrons, because the protons are so much embedded inside the nucleus that it's very hard to yank them out and get to work with them. You do that probably in nuclear physics, where you get into the nucleus and things like that. But most of the times we deal just with the electrons. That's why all of the electrical charges and everything else deals with the electrons, because they can be extracted and actually moved around and things like that. If I have a metal in here, this metal, for example, has electrons. That's very easy. You can move them around. You don't really require a lot of work to have them move around, okay? But they're actually attached to their protons too. So the protons require some work to actually remove them completely out of the area. But you can move them in here with a small battery, with 3-volt battery. You can move them inside the circuit, and you will actually see a current going through that thing there. So that's in terms of, the key thing in here is the electronic charge, E. E for the proton or the electron, it's the same number. That's a good number to remember. 1.6 times 10 to the negative 19 coulombs. This was done an experiment by Millikan and other people, and they found that this is basically the building block of charges. Two things you need to remember about charges. First of all, they are discrete. They are not continuous, and they come in increments of E. Charge are discrete. They're always multiples of E. Okay, that's one thing. The other thing also, they're conserved. Charges are conserved. Meaning, if I start with a certain number of charges, that's how much I'm going to end up with. And this conservation is very, very important to remember, is a local conservation. When we deal with Maxwell's equations down the road, this term local will be a key to understanding the equations and basically summarize them and do stuff with them, okay, and try to solve them. So those are the two things in here. So there is a conservation of charges, and the fact that the charges, they are multiples of E, and E is that number, which is 1.6 times 10 to the negative 19, okay? So, and the unit of charge is the Coulomb. Khawaja, I know you're here. I'm sorry, did I say your last name? I probably, Faraz, yeah?
Yes.
Okay. Here is another surprise for you. So it's not just 9.8 is equal to 10, but 1.6021765651352 is just 1.6. I hope you don't have an objection on that, okay? Okay, so so that's important that you remember, guys, that this is a that this is a number that I remember myself, and I hope you guys will remember that. Okay, 1.610 to the negative 19. If you can remember the whole thing, well, probably you have better memory, and you have definitely better memory than me, because that's as far as I can go. So this is the charge that this is some of the things that we need to know about the charges. You really need to remember this thing also about the fact that the charges are conserved for the case when we do the electric circuit down the road, chapter 24, 25. So you really need to understand that, because there will be charges moving around, and you really need to know how they split themselves when it comes to places where they can move around. So you really need to have that too. So those are key things that we're going to use them later on. The fact that the charges are discrete is no surprise. Even liquids, for example, when you're talking about the flow of liquids, you have tendency to think that's a continuous process, but that's not continuous. As a matter of fact, you know that water is made up of H2O molecules. So that's also a discrete process. So this is, we look at it from macroscopic perspective and think that this is how much we have, but in actuality, it comes in bits. And that's exactly what this thing is. Again, charging objects in here, you can use mechanical processes. Have you guys had a chance to deal with the Van de Graaff machine? Did any one of you see the demonstrations live done or not? Okay, if in case we meet again, I think every campus has one. I'm not sure. I've never been to the campus yet. So I'm new, by the way, to Norco. So there is a Van de Graaff machine that basically builds the charges. And if you go to the science center where the hair basically, it's not going to happen with me. I don't have much hair. So okay, where the hair goes everywhere, and you will, that's basically how you can build charges. But of course, there is more advanced ways of making them. And that's basically some of the things that, did I stop sharing? I think I did. Yeah. So, and if we go back into that course things, I give you to do. When I say to do, I expect you guys do those things, okay? So in the to do sessions, you're supposed to be doing them. So please take care of those to dos. And those to dos are examples from the textbook that you're going to go there and basically follow the example and rewrite that example and do them. Okay, we're going to do some of them in here, and you will see that I'm going to be modifying some of those things as we go along. So that's something that you really have to remember. Okay, so in this case in here, we're trying to use Coulomb's law to calculate the force exerted by two alpha particles, and alpha particles are basically hydrogen atoms stripped out of their electrons. Inside the stars, for example, they're too hot. The electrons are moving; they move away, and you will have basically the alpha particles by themselves. And there are other ways of making alpha particles. Actually, you don't have to go to the sun to find them. They're actually here on Earth too. Basically, so so you have an alpha particle. An alpha particle, think about it, ignore if basically what it is, just take its mass, 6.6 times 4 times 10 to the negative 27. So it's 6.64 times 10 to the negative 27 kilogram. We have to use SI. And I know I didn't mention something about the unit for the charge. The charge has a unit of Coulomb, okay? So that's not a fundamental unit. If you guys remember from physics 4A, the fundamental units are the meter, the kilogram, the second, and the ampere. There is no mention in here of Coulomb. You will learn later on that the Coulomb and the ampere are related to one another, and we will see that down the road. But for right now, just take it as a Coulomb. That is the unit for the charge. Down the road, we will refine our units and talk about the ampere as the unit for the electric current. And you will see that the charge and the ampere, they will be related down there and there. So it's very important. If you cannot attach a unit to it, as a matter of fact, if you cannot measure it, to go back to the issue that was raised initially, it's not physics. So you have to understand that. It's probably math or philosophy or other things. Physics is all about measurements. If you cannot measure it in the lab, if you cannot do observations on it and get a quantity that is represented in terms of units, that is not physics. And there are instances in physics where we introduce non-physical concepts to do things like the center of gravity, which has nothing to do with physics, but we introduced it because we need it. And the same thing in some other concepts. But in here, the mass is a real. So this is the mass of the particle alpha. Also, they tell us its charge, and its charge is because we take 2 electrons from the helium. Basically, we'll be left with 2 positive charges for the to the 2 protons that are left in the nucleus. So the charge now in this case is Q is equal to just 2e, or 2 times 1.6 is 3.2, 10 to the negative 19 coulombs. And the task we're asked to find is the following. We have 2 alpha particles, one next to one another. How far apart doesn't matter. Okay, as long as they are next to one another. And we're trying to find an estimate for how big this electrostatic force that Mr. Coulomb had provided us compared to the force of gravity that we know and love from physics 1, that binds the entire universe together, the solar system together, the galaxies together, and everything else together. So that is the force of gravity that does this thing. But now having 2 alpha particles next to one another at a certain distance, so we have alpha 1 and alpha 2, and the distance between them is r. Of course, they have the same charge, so they're repelling one another, but the force of gravity is trying to bring them together, so which one would win? So that's basically the challenge. We know the electrostatic force in this case, E, Fe, is given by this expression, 1 over 4 pi epsilon naught times times Q1 times Q2 over the distance squared. We know from the physics 1, the force of gravity that you all know also, is the constant G, that's a negative number to integrate that they're attracting one another, times the mass of the first one, the mass of the second one divided by the distance squared. Okay? If I want to find the strength of one versus the other, I can subtract or I can divide. So I'm going to divide. Here is why the distance doesn't matter. If I divide, the r's cancel. And that is one of the beauty for it, that nature has provided it with 2 forces that follow the 1 over r squared rule. That is probably a coincidence living in this 3-dimensional universe, but that's a discussion for another day. So that's probably a good discussion for physics 3 as a topic for discussion. Anyway, how big the force, the electrostatic force versus that of gravity? Again, when you do the ratio, the r squares cancel. Okay, this and that one cancel. So the only thing I'm left with is 1 over 4 pi epsilon naught times Q1 times Q2 divided by G times M1 times M2. So that's the only thing that is left. So here is what we have. 1 over 4 pi epsilon naught times this product of the 2 charges divided by the product of the 2 divided by G, I'm sorry, times the product of the 2 masses, M1 times M2. Okay. 1 over 4 pi epsilon naught, again, everybody need to have an idea of what that is. I think it's in the notes for the lecture in the online, on Canvas. But 1 over 4 pi epsilon naught is roughly, and this is a number I use all the time, 9 times 10 to the power 9 SI. So when I say SI, forces are in Newton, distances in meters, everything is in there. So if you're curious to find out, it's actually Newton times meter squared per Coulomb squared. Okay? So that's what that constant is. So that the meter squared cancels the meter squared, and the Coulomb squared cancels the Coulomb squared, and the unit of the force are actually in Newton. So it's 9 times 10 to the power 9. So we know that. G from physics 1 is what? 1.67 times 10 to the negative 11. From now on, actually, I'm going to make something that probably will make some of you probably not too happy. 9, I'm going to make it equal to 10. So it's not 9.8 that I'm going to make to 10. This whole 9, I'm going to write it as 10 to the power 10. Okay? Because all I am after is actually an order of magnitude, okay? So this is 10 to the power 10. This is 10 to the negative 11. This is, I know it has in here some numbers for Q1, which is 3.2 times 3.2 for, that's 9 times 10 to, so what we are after is just an order of magnitude, okay? So what we're saying in here, 10 to the power 10, 1 over 4 pi epsilon is 10 over 10, not 4 pi epsilon naught, okay? Times the product of the two charge, 3.2 times 3.2, which is 10, times 10 to the negative 19 times 10 to the negative 19, that's 10 to the negative 38. Divided by the product, by first of all 10 to the negative 11, coming from G, times the product for the masses. The masses are, what were they? 6 times 6 is what? 30, which is 10, times 10 to the negative 27 twice. So I have another 10, because 30 is 10, okay? Roughly 10, okay? Because we're just going after the orders of magnitude. Times 10 to the negative 27, which is 10 to the negative 54. Having said that, this 10 and this 10 cancel. This 10 to the negative 35 and 10 to the negative 38, positive 10 and negative 38 is negative 28. And negative 28 and negative 11, negative 11 and negative 28. So I'm going to be left with, what, 17, negative 17. And negative 17, when you divide it by negative 54, 37. So it's about 10 to the power 37. If I made a mistake, please correct it, okay? Here is the deal. This force, so the ratio of 2 newtons is going to be no units, okay? Because this is in Newton, this is in Newton, and basically I'm just getting an order of magnitude how big this one is. So this force, the electrostatic force, will dominate by far and large the attraction of those 2 alpha particles due to gravity. So if you tell me that you have 2 alpha particles sitting one next to one another, what is, I think I did a drawing earlier for 2 alpha particles. Yeah, here. So if they are attracting one another due to gravity, they will repel them one another with a force that is 10 to the power 37. That is a big number. That means that the force of gravity has 1 followed by 37 zeros, bigger for the case of the alpha particle than the force of gravity. Okay. So do you guys see the strength of this force and how dominant it should be? Yes? Very good. So it's a very big force, okay? Which prompted Mr. Feynman. By the way, he's one of your resources also for this class too, Feynman lectures, and they are free also online, is to ask a question. Why in the world, since it's so dominant, why do we see the gravity, the force of gravity then? Why do we experience gravity altogether? Why can't we, because it's so big, it's not just, it's not a million times bigger, it's not a billion times bigger, it's not a billion times bigger, it's not a trillion, it's so big. I mean, it's incomparable between these 2 forces. So this is a force that is so big that you cannot really think about in terms of the force of gravity. The question that to be asked then is, first of all, why the alpha particle exists as it is? Because it has 2 protons inside its nucleus. And the answer to that should be in physics 3. So that should be easy, because there is actually a far more powerful force than this one, namely the nuclear force that glue together the nucleus. So that answers that question. But the question to be asked is, okay, we live on Earth, for example, and our daily experience is dominated by gravity. We get tired because of gravity. We try to basically jump. We cannot jump as high because of gravity. And everything we do is on a daily basis dominated by this force of gravity, which amounts to tiny, tiny fraction compared to the electrostatic force. So the answer in a nutshell, does anybody know the answer? Let me give you about a minute or 2. Why in our daily experience we deal more with gravity than this force, which is supposed to be big. No? Okay, no problem. It's because the electrostatic force always comes neutralized, okay? If you take fraction of a percent from all of the atoms that makes us and make them ionized, meaning they lose their electrons, for example, we will all repel one another and we will never be able to communicate with one another, basically. It will be impossible because of the electrostatic forces that will be so big of a force. So that is really in a nutshell why that force of gravity dominates, and dominates even on a large scale, for example, in the case of the universe, because everything that is in the universe comes in with the charges that are completely canceling one another. The only places, for example, where gravity and the force of electrostatic force and other forces are working against one another, in the case of stars, for example, because gravity is trying to put the star, basically collapse the star on itself, because of the heat that is generated by nuclear forces inside, that is repelling the material outside, and the star more or less for most of its life cycle stays in a stable configuration during that time. At some point we'll run out of fuel, which in that case gravity will win again, because again there is nothing in there to keep gravity from taking over, and you will have so much dominant things. So that's in a nutshell basically to answer the answer to that question. So let me go back into this the same session? Yeah. So that answers this example. You see the discussion I generated from this example? The point is, you saw the problem, you read the problem, you tried to understand basically what was given to you in the problem. This is actually a practical step-by-step on how to do these things. Things we know about the alpha particle, things that we know for the force of gravity and the force of electrostatic force. Those are the things that we put together. Now, this is a step-by-step solution, justifying the steps that we did, canceling factors, entering numbers, and we found a number. So this, we answered the question that was prompted from us. So we solved, we justified the solution, and then we found the answer. Once we found the answer, we generated the discussion after that. We asked a question then. Do you guys understand that? So that is, in a nutshell, how we solve problems in here. We take the problem, we try to understand it, try to collect the data from it, wanting to follow the things that were asked, pull what we know. In this case, this is what we know, and then solve the problems. I know I didn't write, but you're supposed to be writing the steps, step by step. Here is my justification. Cancel the R's. Place the values of these things. I said 9, so I went a step further for us than what you guys did. I said 9 is almost 10, okay? Because all I am after is actually an order of magnitude. So when we say an order of magnitude, how big it is, that's all. I mean, I probably, if you did the math, you may find 1.7 times something or something. That's really irrelevant compared to 10 to the power 37. Or 0.2, which brings this number to 10 to the power 36 or something. So all it did was just a rough number, okay? Which I don't even need a calculator for this thing in there to do it, okay? If I'm just good enough, probably. I think I made a mistake in here with the numbers. But if I'm careful enough, it should be easy to get that answer much easier, okay? But once I found the answer to the question, then we generated a discussion from that. So this is a practical example on how to do these things too, okay? The other example is, I probably skipped one in here, which should be easy enough for you guys to do. Example 21.3, the electrostatic with superposition. Now here is the challenge, okay? By the way, this question is important for you guys, okay? So that you need to understand these things in here. Mr. Coulomb's law talks about two charges, Q1 and Q2, that's all, okay? So that's what Mr. Coulomb's law says. You have to have charge Q1 and charge Q2 in here. So the question in here that is going to need to be answered is, what happens if you have a third charge Q3 in here? And you would want to know the strength of the force on Q3. How are you going to proceed? There is nothing written in Coulomb's law that tells you this is how you do it. It tells you only about two charges. It doesn't tell you about three charges. It tells you only about two charges, charge 1 and charge 2. Working against one another, you want to force on charge 2, this is how you proceed about doing it. You want to charge 1, you do the same thing, except just you reverse the symbols, that's it. And you're done. That's all Coulomb's law says. Now, the challenge is you have a third charge that comes into the mix in here, okay? If all the universe is made up of only two charges, you're done. But the universe has the habit of bringing things in a huge number, okay? So you really need to deal with that. So on charge Q3, the question is, how do you find the force still on 2 due to Q1 and Q3 in the same time? There is no answer to this one. And the answer, we have a feeling it should not work, yet it works. And that is called the superposition principle. The superposition principle is the following. Ignore Q3, basically, and find the force that Q1 exerts on Q2 by itself. So not having Q3, although it's there, will give me the force on 2, but due to the charge 1 only by itself, basically having isolated Q3 momentarily, is 1 over 4 pi epsilon naught times the product of the charges Q1 and Q2 divided by the distance between 1 and 2 squared, and that unit hat that emanates from 1 to 2, unit vector hat, r hat, okay? Now repeat the process by ignoring Q1 now. Q1 doesn't exist. Just find the force exerted by 3 on charge 2, ignoring Q1 altogether. So we're going to find the force on 2, but now due to charge 3, not due to charge 1, because we don't have charge 1. At least we hid it. We put it under the blanket for a moment. So it's 1 over 4 pi epsilon naught times the product of the charges, namely Q2 and Q3, divided by the distance now between 2 and 3. I'm sorry, between 3 and 2. Let me stick to this same notation. Times the unit hat vector that emanates now from, let me get rid of this thing, from 3 to 2. But in actuality, this is wrong. I could not really hide any of the other two charges while I'm dealing with either of the forces. Do you guys understand that? The fact that Q3 is there should impact this force, but it doesn't. The fact that Q1 is there should impact the second force, but it doesn't. And what we say in this case, the total force now exerted on charge 2 is simply the sum of the force on 2 coming from 1, as if 3 doesn't exist, and the force on 2 coming from 3, as if 1 does not exist. That's it. Add the two forces. Let's say, for example, this is how the first force is. This is the force on 2 coming from charge 1, assuming that Q3 is not there. And this is the force coming from, let's say, for example, on assuming that Q1 is not there, and now use the vector addition to find the force on 2. That's it. That is the superposition principle in a nutshell. The reason why it's a principle and not a law, that should not work. There is no reason for it, it should work, yet it works. That's how things are, okay? So that's, did you guys do waves when you did physics 4A? Because I'm not familiar with the course sequence for you guys in here. Did you guys do waves? Waves in the case of the, not the harmonic oscillator going up and down, but the case of the waves on string, for example, or the waves in the case of sound waves or something like that? No? No, okay, you didn't do waves. When you do waves, you will find another superposition of waves, but that superposition is real. There is a justification for it. There is a proof for it, mathematical proof for it, that that superposition works. You have a wave coming, for example, from one sound, and another wave from another sound source, and you combine them, and you will have a different sounding wave that has probably different frequency and different amplitude depending on how these two waves come in. So that is a principle that obeys mathematics, and it's not a principle, it's actually a law in that case, because you can prove it, and the proof for it is not hard to do at all, because the equations, the underlying equations that govern waves are actually linear in nature, so adding them will give you addition. This is not the same though. This superposition now, theoretically, it should not work, because the fact that charge 3 is there should modify a little this force. I cannot think that this force should be the same. It should be slightly different, yet it is not, as if the other one doesn't exist at all. So we cannot really promote it to a law because of the fact that we cannot justify it. Okay, but it works. Okay, so that's the key thing with it, is that this is okay. Superposition principle is going to be from now on, and I say that to all of my physics 2 classes, your BFF. So forget whatever your best friend is. This is your BFF forever. You're going to find it very, very useful in the case of electrostatics, in the case of magnetostatics also, and even in the case of electrodynamics and magnetodynamics. So this principle is a very useful principle, and you have to remember it. So basically what it is just ignore these things, and you just find the forces due to the different charges and add them up. Once you add them up, now you have the entire force. So that's exactly what this example is, and the next example. So I'm going to ignore even example 21.3 because it gives you two charges on the same line and trying to find the force on them. Or maybe we should do that. Doesn't matter, one of them. And the other one does it in the case of the two charges sitting on one side and the other, and you're trying to find the force on the distance from them. So 2-point charges are located on the x-axis. We still have about less than 10 minutes to finish this session, and then we'll go on break. Located on the x-axis of coordinates, so they're on the same line. Q1 is 1 nc. When you see the n next to a unit, that means a nano. That's 10 to the negative 9, okay? And Q2 is a negative 3.0 nanocoulomb, okay? At x equals to 4 centimeters, whereas the other one is x equals to 2.0 centimeters, okay? The question is, what is the total for electric force exerted by Q1 and Q2 on charge Q3 at equal to 5 nanocoulombs at distance x equals to 0? This is what I'm going to do in here. I'm going to do everything like everybody does in physics, and that is to make a little bit symbols in here. So I have a line in here. We have Q1 in here. We have Q2 in here. And now we brought a Q3 in here. Okay. And Q3 happened to be exactly at the origin. Q3, which is 5 nanocoulombs, is at x equals to 0. Whereas Q1 is at positive 2 centimeters, and Q2 is at negative 3 positive 2 centimeters, and the other one is at 4 centimeters, okay? So this is wrong than what I drew in here. So this is where Q3 is. So this is at a distance 2 centimeters, this is at a distance 4 centimeters, and this is at the origin, and this Q3 is 5 nanocoulombs, and Q1 is negative or positive 1 nanocoulomb, and the other one is a negative 3 nanocoulombs. So this is 1 nanocoulomb, and this is a negative 3 nanocoulomb, okay? So I have all of the units basically in a graph, okay? It helps to put graphs, okay? So it's a very important technique to use in physics. We're supposed to find the force on Q3, okay? We're supposed to find the force on Q3. Well, I could do the same. The following. I could choose the x-axis in here, okay? And I'm going to put Q3 not at the origin. I'm going to put the Q3 actually at some origin, okay? At some coordinate x, okay? It's in centimeters. And I'm going to use Coulomb's law to find it and put x equals to 0 if you wish. So we could come back later on and do this problem at x equals to 0. So that's something that, so the forces, as long as the charge is not sitting on one of those 2 centimeters or 4 centimeters, should be good. So you have to remember that, okay? So I'm changing a little bit the problem from what it was stated. So the force on that charge 3, everything is in the same direction. If it is here, this is an attractive force, whereas this is a repulsive force, okay? One of them is attracting it, and one of them is repelling it, okay? So the forces will be with different sizes. That is, if x is less than 2 centimeters, the Q2 is pulling toward it, and the Q1 is repelling it because Q1 is positive, okay? So there is a point in between them where the force has a potential of being 0. So it would be interesting to find that point in there. If I put it in here, Q3 is still attracted, and this one also still repelled. So there is a position in there where there is a probably they could cancel, maybe, okay, depending on the solution of the equation. If you put it in the middle between them, somewhere where I initially put it, which was a mistake, now I know, this one will pull it towards it, and this one will repel it from it, okay? And the force can never be a negative. So I'm going to assume that it's at a position x in such a way that is actually, I'm going to put it positive, but outside of x equal to 4 centimeters. So I know then Q3 is going to be negative, Q2 is going to be negative, and Q1 is going to be positive, and I'm going to just add the two forces, okay? So it's 1 over 4 pi epsilon naught times, let's start with Q1 first. Q1 times Q3 divided by the distance between them. Remember, this is at the position x, and this is already at 2 centimeters away from it. So this is going to be x minus 2 centimeters to find just the distance squared. But don't forget, this is in centimeters, so I have to multiply it by 10 to the negative 2 squared. So it's going to be 10 to the negative 4. Remember, x is in centimeters already, okay? So this is the force that is positive. The force that is negative is coming from this one, Q2. So I'm going to assume an x in here is more than 4 centimeters, okay? Minus, because the other one is negative, so it's going to be in the negative direction, minus Q2 times Q3 divided by x minus 4, the whole thing squared, and don't forget that conversion factor of 10 to the negative 4, okay? So that takes care of my, somewhat my problem. Q1 is in nanometers. Q3 is in, nanocoulombs. Q3 is in nanocoulombs. Q2 is in nanocoulombs. So I'm going to take the nanocoulomb squared, which is 10 to the negative 18 outside, okay? And I'm going to deal now with Q1 as just a number. Remember, Q1 is 1 now. And Q3 as just a number, a positive number, that is 5. And Q2 now, I already accounted for the sign in here. So if I do it again, it's going to be a double jeopardy. So I cannot use that number now again. So I'm going to use the Q2 now being 3 coulombs. Okay, I already took care of this negative sign in here. And Q3 is still 5 coulombs. So I'm going to put the numbers now, paying attention to what I'm doing. So F on 3 will become 9 times 10 to the power 9 times 10 to the power 4, coming from that conversion factor. Remember, 10 to the negative 4 times 10, when you move it up, it's going to be 10 to the positive 4, times the product of the 2 nanocoulombs, which is 10 to the negative 18, okay? What I'm left with is, also I have Q3, which is a common factor, which is just 5. And I'm left with the following expression. Q1, which is 1 actually, 1 over x minus 2 squared minus Q2 now, which is 3 minus 3 over x minus 4 squared. If I put it on this side, the whole expression will hold true, the same thing, except now I'm having I will have a negative sign, that's all. Because the force should flip now, because due to this one will be in this direction, whereas due to this one is going to be the other. So these two signs will just be the same force, except it's going to be the different signs, that's all. So having this expression in here, I have 5 times 9, that's 4.5. I have 10 to the negative to the power 9 times 10 to the power 4, that's 10 to the power 11. And you have in here 10 to the negative 18, so that's going to be 10 to the negative 7. But I have 4.5 times 10 to the power 1, so it's going to be 4.5 10 to the negative 10. So that takes care of the math. Please verify all this math, okay? I'm just doing it in here for... And then I have this expression. Okay. Now this is a modification than what the example was in the class. Oh, I'm sorry, we ran out of time now. Probably we should continue this discussion later on. Any questions? I will continue this discussion later on, finish it quickly, and then we will talk. We're not going to spend more than an hour later on in the lab, so please do join me. And I know this is the first session. I'm not doing that discussion question like I said. So please join me around 2:30. Remember, the link to that session is not the same. It's a different link, okay? And it's on Confer Zoom. So please go and get yourself coffee or water or something, and let's finish this one in the lab session. Good? Very good. See you guys.